we can start with recording the screen to perform this exercise. I want to create this frame with these columns, the HB columns, and these beams, double T beams. The first step is to create the new model again. Pay attention again on the Unity. And I can start with blank model or grid only model, is the same. Now it's not important these values because I will modify it later. Okay, blank model. I can start with the grid. Right click on the screen, grid data, modify. Okay, I want to create this grid, so we have 5 meters, so starting from the left, 0, 5, 10, 15 in the X direction, and 0, 4, 8 meters in the zeta direction. I'm not interested in the Y direction, only X and zeta. So pay attention, I choose at millimeters, so I have to put 5,000. Okay, this is the grid. Put the view in the X zeta direction. And I'm going to create an analysis. So in analysis option, I'm going to create an analysis that is performed only in the X zeta plane. So I'm not interested in what happened out of plane. So as you can see, the available degree of freedoms are only the ones in the X zeta plane. Okay. That means if you put a forces perpendicular to the screen, nothing will happen because this frame will work only in the plane of the screen. Okay. As last time, we have to define the material. We can start with a new material. It's not important. Steel, okay. This steel with this NTC, okay. Perfect. Modify the material in order to put the Young modulus, that is the elastic modulus, equal to the one of the steel, so 210 gigapascal. We have Newton and millimeters, so you have to put megapascal. Poisson 0.3, and the weight of the steel, of course. For now is not important these parts, the part of the plastic properties like the yielding stress, the ultimate stress, because I want to perform only a linear analysis. If I'm going to perform nonlinear analysis to consider also the link, I'm not interested in nonlinearity of the members. So my nonlinearity will be only in the connection. So member will be elastic in this analysis. So it's not important now this value. I can put everything here. Okay, again I have to import the cross section. So section properties, frame sections, import new property, double T because I have IPE and HAB. You have the list Euro. because these are European profile. Okay, I'm looking for these profiles. 120B, perfect. Okay, and again the one for the beams, 330, perfect. Again, check with the manual, with the theoretical value, the properties, the cross-sectional area and the moment of inertia and so on, because if you are because something is not equal to the theoretical value or manual value, you can modify it manual by set modifier. I'm going to put now modifier in order to not consider the shear deformation. So I'm going to put very high value in this shear area. For both profile. Okay, now we can design our frame. Draw frame. Pay attention here to have the correct profile selected and that is continuous and not with releases, because the releases will add it after. So everything is continuous now. Starting from the bottom to the top. We can create a point by point the member, or we can use the replicate option that SAP give us the opportunity to copy and paste the profiles. I can choose these two profiles, going in replicate. As you can see, we have the type of increments. So I can say go in the X direction by a distance of 5,000 millimeters and the number, so for 3 times. And I have created all the columns in this way. Now I can create the beams. From the left to the right. Again, I can create it point by point, or I can select and copy. There is a trick in SAP, in all of the software, finite element software. You can select the beam or the columns by using some properties. For example, by using the sections. So you will select all the elements with the same section, or by using the material, selecting all the elements with the same material. This is very important because when you have a huge frame with a lot of elements, you can select all the, for example, EPE 330 beam. I can copy it again, replicate, in the zeta direction, minus 4,000 millimeters, 1 time. Okay, I created my frame. Now check the local axis or the 3D view in order to be sure the orientation of your members. Okay, this is the right orientation. This weak axis is always in the other direction, out of plane, and the strong axis work always in the plane. To have a more refined results, I can divide these frames, the beams, into different elements. Oh, sorry. Edit lines, divide frames, and I can choose like 4 to have more than one elements for the beams. You can check always also the properties and the number of your elements by using this command that are set display options. So I can choose what kind of option I wanted to see in my frame. For example, I wanted to see the frame section in order to see if I choose the right section. And you have everything. You can see the cross section and everything. We can see also, if you want, the number of nodes and the number of elements, of course. Now I'm going to put the external restraint, fixed one, because in my example everything at the base is fixed. You just need to select the joints at the base, select everything for the fixed one, and apply. This is the classical symbol to indicate the fixed joints, external fixed joints. Now we can put the loads. So again, first of all, we have to create the load patterns. I'm going to create 2 different loads, vertical and lateral loads. I don't want to consider the self-weight, so I'm going to create a live load with 0 in the self-weight multiplier for both vertical and lateral. So now I can assign the loads, starting with the lateral load, forces, so joints load, forces, lateral, global direction, pay attention in global and local direction, now is global direction. I'm going to put 2 lateral forces, like in the scheme, that are equal to 93 kilonewton. So I have Newton here, so 93 multiplied by 1000. Okay. Now the vertical one are distributed loads. So we have the option. If you want to select all the beams, again, you can select the beams by properties, or you can use these select lines parallel to. All the lines that are horizontal will be selected. Then we have to select frame loads, because these loads are on the frame, are on the beam, and distributed. Pay attention to choose the right vertical, global direction. Don't select gravity because it's not so, it's better to not use gravity because depends on your model direction. It's not, gravity is always on the zeta for SAP. So if your model is not in zeta as vertical, maybe it's not useful for you. Select always the direction. So I'm going to put a force a distributed force equal to these values 123.6 kilonewton on meter, but I have Newton and millimeter, so I have to convert from kilonewton to meter to Newton to millimeter. For this case is the same. These last parts regard the trapezoidal loads. If you want to put a load that is with a different value from the start to the end of my beam. If I have this kind of loads, I can use this task. Okay, apply. Sorry, there is a minus. I have to put a minus here. Now if you put replace, this load that I have put before will be replaced by the new load. If you select add, the new load will be added to the previous one. For example, if now I put add, previous I have put at plus, now I am going to put minus, the results will be 0. If you put apply, if you select apply, you will have 0. And of course, if you put delayed, you don't need to insert anything, but this load will be deleted. Okay, I'm going to put replace and apply. Okay, I have the vertical and the lateral load. Now I can select the analysis type, the load case, and I want to perform linear static analysis, buckling analysis, and second order analysis. Starting with the static, linear static for this case, and I'm going to add lateral and vertical. Okay. Again, new load case, buckling, again lateral and vertical, 6 modes. Okay, we are interested in the first one, and the last one is nonlinear by considering the p delta effects, the geometrical effects, the geometrical matrix. So second order nonlinear. So nonlinear with p delta. Again with vertical and lateral. Okay, everything is done. I can perform the analysis by using this button, play button, or by using F5. I have to save the model. we can look at the results. I expected a buckling of 9. I can go and show the former shape, buckling 9.06. Okay. I can create a table I'm going to put in my table this first case is a rigid case because everything is continuous. Rigid, buckling. And semi-rigid. Buckling, delta 1, delta 2. And I can put also flexural moment at the base. Okay, buckling is 9. Voi avete provato a fare un'analisi?
Non il buckling.
Cosa dice?
E non fa vedere nulla. Cioè non computa proprio.
Quanto... Ok, dopo guardiamo. We are going to check the first order displacement. Linear static. You can see that the maximum displacement is 35.777. This is first order and second order. First order and second order. So the maximum is 35.8. And for the second order, I can use, for example, the simplified equation that you see with the critical load that is 9. We can know the amplification of moments and displacement. So amplification will be the critical load divided critical load minus 1. 1.12. So the first order displacement is 35.8. I expect the second order displacement equal to more or less, because it's a simplified approach, this one, 40.3. You can put displayed, show the former shape, or you can push F6. Second order, nonlinear. We have 40.0. Perfect. Now I want to show you a method to estimate the buckling multiplier without performing a buckling analysis, but using only a first order analysis. This is the Horn method, metodo di Horn. In the Horn method, tell us, starting from the displacement, we can estimate the buckling. Delta 1, delta 2. And this is the equation. The buckling multiplier is equal to phi, that means vertical divided by horizontal load, and no, sorry, horizontal divided by vertical load, divided by the maximum between the ratio between the displacement, but is a delta displacement, and the height of the column. So we can do for our frame the height of the columns are 8 first plan and second floor are 400 millimeters because are equal. Then we know the displacement of the first and of the second. The second is this 35.8 and the first is 20.5. Now we have to compute the delta. So the first is the same because first minus 0, because first related to the ground floor are the relative displacement. For the second, we have to do the top minus the first floor. So the delta are this minus 0 and this minus the other one. These are the delta. So we can apply the equation because now we know we can compute, for example, the total horizontal load that is applied in the nodes are equal on both floors, 93 kilonewton, so 93,000 Newton. And we can calculate the total vertical load. Because it's 123.6 multiplied by the length, the resultant of the force. That is the same in both planes, in the first and the second floor. So I can compute the first term, phi, horizontal divided by vertical, and I will have two different second terms. The relative displacement of the first divided by the height of the first floor, and for the second floor the same, so the second term. This divided by the height of the first floor, and this divided by the height of the second floor with respect to the first floor. So at the end of the procedure, the critical load will be this divided by this and this divided by this. The critical load will be the minimum between these two values. So with the Horn method, we have 9.7 without performing any buckling analysis. È chiaro quello che ho fatto? Fare gli spostamenti relativi, altezza relativa e carichi verticali agenti e orizzontali agenti ogni piano. Ok.
Generalmente si usa, cioè si fa tutto lo studio della formazione, si usa questo o si usa questo metodo?
Questo è nato negli anni indietro quando il buckling non era disponibile in tutti i computer, oggi si fa il buckling. Anche perché applicare questo metodo in un telaio molto più complesso inizia a essere laboriosa la cosa. Ok, now I can show you the first way to insert the semi-rigid connection. As I told you before, you can select the releases. So we can create two different groups. So create assign to group. You can define a group. With this group we can put some type of elements in a group in order to select it with one command without selected by hand. I can create a start beam and another group that are end beam. Now I will show you why I'm going to create this group. Okay. I'm going to select only the first part of my beams starting from the column I'm going to select only these beams because I want to create releases in these beams, not also in this, only in this and in this part of beams. Of course, if you have only one beam, I have 4 elements. If you have only one element, you can select directly the element. I can assign to a group, this replace to a group.
Ma quando io seleziono non mi fa selezionare solo un pezzo, mi seleziona tutta la slide.
L'hai divisa?
No.
Devi fare edit. Delle travi, io sono delle travi. In 4 elementi. Now I assigned to a start beam these initial beams. So if you press Ctrl plus G, you will have select by groups and you can select these beams. See that I have selected only these beams. I can do the same with the other part of my beam. So I can select the end beams. Assign to a group, end beam, and replace apply. Okay, now I can select or the initial part of the beam or the final part of the beam. This is important because when I want to create a release, I have to say if this release is in the start or in the end of my element. So now I'm going to select the initial part of the beam, Ctrl plus G, start beam, select. Now I selected only these beams. Assign frame. Now you can assign the releases, partial fixity. You can see here the releases. This is the table for the releases. As I told you before, you can release all the degree of freedoms. If you will have a program with 7 degrees of freedom for each node, you will have also the warping releases. Now we have 6 degrees of freedom each node, so we have 6 releases. To be sure in which releases you are interested, you have to check the local axis, not the global. So I'm going to check the local axis before select a releases. Local axis. You can see the red one is the first, the direction 1. We have direction 2, and direction 3 is perpendicular to our stream. So to create a nonlinear behavior in this moment in the plane with the rotation around the axis that is out of plane, I have to put a releases around the moment 3, in this way. And pay attention, because we want release only in the initial part, so pay attention also in the direction that is from left to right. So start is in the left. If you put 0, you have the perfect hinge. So if you apply with 0, you will have this symbol that is a perfect hinge. If I select also end, you will insert a connection here, a hinge here. So now I don't want this hinge, so I'm interested only in this one. And I don't want to create a perfect hinge behavior, but I need a semi-rigid stiffness. That is this one, the one that I have reported in the PDF file. I'm going to put this value directly in my SAP. Pay attention, here I have kilonewton multiplied by meters. So I have to multiply it by 10 to the power of 6 to have Newton millimeters. I can do the multiplication directly here with A6. SAP automatically will calculate my partial rigidity. And the same thing for the other part of the beam. Sorry. And the beam. This time I'm not interested in the initial, in the start, but in the end. So I'm going to select end, and I'm going to give to the end the same partial rigidity. You can understand if you are performing well, because SAP gives you this screen, this display that you can see here and here the partial rigidity. So we can perform the same analysis, first order, second order, and buckling. I don't have to change anything because the loads remain the same and everything remains the same. And we can check the displacement of the first order that will become greater 60.9 something, yeah. And I expect a buckling that is lower because my frame is more flexible, the displacement will be higher, the buckling will be lower. My frame is more deformable with respect to the rigid one. The buckling is 6.0. I can use again the simplified expression, putting here 6 and putting here 60. I expect the second order displacement equal to 72, more or less. Okay, perfect. Now it's important to check the moment on the connection, the first order moment on the connection, because if you put right click on the element, you will have the diagram of these elements, of this portion, from this point to this point. Here we have moment. You can see the bending moment is equal to kilonewton meters, 207. Why this is important? Because, as I told you, with this type of releases, we don't have any limit on the behavior in the moment. We have only the stiffness. So the moment can increase until the infinity, theoretically infinity can be. Of course, when you have the buckling, you can calculate the critical load of a column by multiplying the axial load multiplied by the buckling factor. This is directly the critical load of the column. So when you need to perform a stability check and you don't know how to calculate the effective length of this element, you can perform a buckling analysis multiplying the buckling factor by the axial load. You will have the critical load. This is an important task. Now we can look at the links. First of all, the question is this stiffness. What kind of stiffness is? Is a real stiffness or is a value that is purely theoretical value? To understand this, we can use the definition of the Eurocode A3.18, This Eurocode define how to classify the joins. So you will have, for the beam to column join, something like this. Here you will have a rigid joint. Here you will have hinge. And here you will have semi-rigid. This stiffness that classify hinge from semi-rigid is equal to 0.5 Young modulus of the beam multiplied by second moment of area of the beam divided by the length of the beam. We can compute the stiffness to understand where if our stiffness is hinge or rigid or semi-rigid. So the Young modulus of the beam is this one. The length of the beam is 5000. The second moment of area, I'm going to check the second moment of area in my properties. This one. I can compute the hinge stiffness. That is this value. I can compare this value, there is our Newton millimeter, with the one that I have used. I have used this value. I can perform a ratio between this value and the hinge value 1, and my value is 5 times greater than the hinge value. So it's a real semi-rigid joint for what concerns the stiffness. To be a rigid joint, this value is 25 times this one. So my joint is something that lies here. Lives here. I can show you also numerically the differences between, if I put a hinge connection, I can show you quickly. If I put 0 in the value of releases, I expect that the buckling will decrease greatly and the displacement will increase. Now I put it a perfect hinge. Buckling becomes 1.1 1.2, so really small. Displacement will be 306. So you can understand the importance of understand the behavior, the real behavior of the connection. Here, if you put the hinge, you will have something that is not possible to realize. Okay, now the last thing, I want to create the link. The main difference between link and release, so we have two main differences. First one is that you have to create physically a link. It's not a property of the beam. You have to create a space for insert a link, and in this space you don't have the property of the beam, but only the property of the link. So this space can be great, must be really small, because if you create a big link, you have a big deformability of the system, of course. And the second task is that you have to define a complete behavior of your link. So I'm going to create a space for a link. I'm going to delete end beams. I can use the groups that I have created before. So now I have deleted of all the final part of the beam. And I'm going to create a grid in order to insert the links. So again, grid data. In the X direction, I have to create the space for the links. In my opinion, 10 millimeters is good for using the links. But you can try and test with different length and try what happens if you use 5 millimeters or 20 millimeters. So the first point is the point of the column, 0. Second point is the point of the link, 10. SAP will reordinate after the grid. Then we have the beam, and we have to create the space for a links on the left and on the right of the second column. So I'm going to create 10 millimeters before and after the second columns, and so on with the other columns, before and after. You can see that near to the column we have this grid that is 10 millimeter in the X direction. You can see. Here we have 0 and here we have 10 millimeters. Again, SAP gives us a trick to modify quickly the grid. You can use the interactive database editing. I want to modify, you can modify everything with this database. I want to modify the system, grid, and data. Okay. Now you can see grid line. I can go to Excel in this option, to Excel, and SAP will open an Excel file in which is more simply to modify the grid and do operation plus 10, minus 10 is more quick. For example, now here I have forgotten 0. Yes, so I can move the points by copy and paste. Okay, I modified my grid. Yes, is right. After you modify without save anything, you can select from Excel. Previously we have selected to Excel, now from Excel. You can see that automatically the values are updated. And now we can do apply to the model. Done. Theoretically, they modify. Is not worked, but I don't know why. Okay. Okay, once we have created the grid, you can see on the left and on the right of my column I have the space for the link. Now we have to create the link. Define section properties, link properties. Of course, new link. And you can see that we have a lot of options. These are all the options that are related to our link. We can create a gap, a hook, a damper, a linear link, a multi-elastic, plastic. You have a lot of options. This is principally for the seismic behavior. To create, you can create also a combination of a link in order to have an hysteresis. You can put elastic with damping, or you can use simply the multilinear plastic. I want to select all direction fixed and give the nonlinearity only in the direction 3, as I done before. You can see that here you can select the hysteresis behavior. This is the isotropic, kinematic, if your behavior is not in this option, if your full behavior is not in this option, you can create a mix between different type of link to have a real behavior. Now we are interested in multilinear elastic. I'm not interested in the hysteresis. So again, in the direction 3, nonlinear behavior, and you can see here we have the curve. This will be the curve of my joint. So I have to put the rotation, the moment in this table. Pay attention on these values, because if you perform a linear analysis, SAP will use only this value and not this value. So if you perform backlink analysis, backlink is a linear analysis, so you will use this value. Okay? I create a joint previous with the stiffness that is equal to the one used in the previous analysis, with a moment that is 60 kilonewton meter. This is an elastic perfect plastic joint. Remember that the moment on the joint was 207. Now I put 60 as a limit. I'm going to put this rule in my joint. Pay attention on rotation and moment. So rotation and moment. You can see that this is an elastic perfect plastic link. And remember to put also the stiffness in the linear part, because if you want to perform a buckling analysis, you have to select also stiffness here. I'm going to put the same stiffness used before. And now I'm going to design the link. Draw two joint link. Link 1, I don't give it a name to the link, from point 1 to point 2. If you want to be sure about the rotation, again you can look at the local axis, not at the global axis. And again you can see that direction 1 is the red one and the blue one is out of the screen, that is the moment 3, that is the one in which we are interested. So it's okay. We can design the beam. EPA 330 continues from the link to the other beam. Now I can select this beam plus link and replicate. In the zeta direction. And I can do the same in the x direction for 2 times. Okay. Again, I can design again the link. In the draw option, you have draw to joint link. From the column to the space for the link. It's better to go always from the left to the right, of course. Sorry. So from the space to the column. And then design the beam. So beam from the other beam to my link. You will have this situation. beam, link, link, beam, with the column connected in the middle. Define replicate 2 times or 3 times, 1, 2 times, okay. Ok. Siete riusciti a disegnare lì? Now I can perform the analysis, but I have to assign again the loads because in these beams I don't have the load. So to display the load, you can display assignment, frame, assignment, vertical loads. You can see that in the new beam we don't have the load. So I'm going to assign again the load. And the last thing is to perform again the analysis and check the results. I want to create a new type of analysis that is the non-linear analysis, but without p-delta effect. Because as I told you, to use the link, the curve, you have to perform non-linear analysis. If you want non-linear without geometrical effect, you have to select non-linear without p-delta, so with no geometrical effect. Okay, we can check the results starting from the buckling. I didn't expect differences in the buckling because, as I told you, buckling depends only on the linear part. So buckling don't use the curve, use only the linear definition of the link. So buckling depends on this value, on the effective stiffness for linear analysis. In fact, the buckling is 6.7. 0.07. If we look at the displacement, starting with linear static displacement, Look at the joints, first of all. You can see if you perform a linear analysis, you don't consider the link because the link is on nonlinear analysis. So if you want to consider the link, you have to perform nonlinear. Then you can choose if you want the second order or not. But to see the limitation on the joint, you have to perform always the nonlinear analysis. You can see that with the nonlinear analysis, the moment on the joint is always less than 60, because 60 is the limit that I put that in the definition of the link. If you perform a linear analysis with the link, you will not consider the link, but only the elastic part of the link definition. And the last thing, of course, the second order analysis with the P delta effect will depend on the link behavior. So you will have the limit of 60 on the joints. You can also see directly the results on the link. If you go in display forces, you have links. So you can see directly on the links the results. This is the value of the moment for the linear static without the selecting of the nonlinearity that are really high. But if you look at the linear static with the selection of the nonlinearity, you have the limit of 600. That is the limit that we used for the link. This is an example. Then we have to define a more refined bin to column connection. Is not a real connection I created. Is not perfect. Okay, do you have a question about the one sul link?
Uno però sicuramente come faccio a scegliere la rigidezza iniziale da usare nel modello? Cioè se nella realtà io il tipo di connessione lo decido in base alla reazione che ho, però a priori quando sto modellando non so ancora